Okay, we are back. It's Friday. We'll try to have some fun today in spite of the weather and test one. See if we can overcome that. Yeah, we're just reviewing today. No new material. We'll start chapter 19 on Monday. So in your spare time this weekend, be reading ahead into 19. Today through Monday, the test is already over there, 16 through 18. Yeah. Anything else business-wise? We're grading quiz 3 today. We'll post the key if you want to see the key for quiz 3. And as always, you have to, we don't make any marks on your turned in quizzes with the COVID thing. So you have to look at the posted key and then see where we may have taken off points. That's the best thing we can do. But we will be handing back your tests. I'll talk about that next week when we hand back tests. We do have the hand back slots out here. Okay, anything on that? Okay, we got a bunch of problems up here already. Let's start with the first panel up there. Guys here in person are already working on it. If you're watching the video, you can pause your video, of course, and work through these and see if you get them right. So kind of calibrate your understanding. We got a couple new ones up here, maybe. Some people were wondering about phosphate we saw there. Oh, and we have dimethyl sulfide there as a directing group. So here we have cyanide on the benzene ring, and we're brominating. So what type of a group is cyanide? Meta-director or orthopara? Okay, some people are meta. Yeah, meta, because it is conjugated. It's a triple bond here. It's conjugated, so that's partially positive carbon due to resonance. So you'd want to go to the meta position, okay, to avoid placing the intermediate cation next door to that electropositive. So what would the meta look like? Cyano and meta bromo. Yeah. Okay. Yep. And then we've got the sulfide. Now, what's on sulfur? It's isoelectronic with oxygen, right? Right below oxygen on the periodic table. So what do we say here? Well, these lone pairs can do what then? Is it a orthopara director, a donor, or is it what's wrong? Yeah, the lone pair is right on a heteroatom, just like oxygen and nitrogen. So we'd predict that this would be an ortho para director. And we're doing Friedel-Crafts acylation there. So I think that plus ortho would be, if you want to draw ortho also, would be the correct answer for that one. All right, and then let's go up here, the one-step ones first. We got bromobenzene, and we're sulfonating. And remember, the halogens are inductively, through the sigma bond framework, electron withdrawing. They're pulling electron density out of there, but they have the lone pairs still. So their directing effect is actually orthopara still. So we would draw, what, the bromo sulfonic acid plus ortho, although I think ortho is kind of minimal here. Bromine's a pretty big atom, so it starts to block the ortho position. And don't worry about that, okay? If it's an orthopara director, if you want to draw both of them, that's fine. Or just draw one and say the other's also there, okay? But don't draw meta if it's an orthopara director. Okay, these positions are important there. Okay, what are we going to do with phosphate? So this is kind of a biological example. Phosphates are more common in biology. And I've drawn out the whole phosphate structure there. So predictions, orthopara director or meta director? What does it have right on the ring again? An oxygen with lone pair. So what's your prediction here for nitration of phenol phosphate? What would you say? It must be the orthopara product. Yep. Yeah, you can get that. I won't draw out the whole thing here. PO3, Me2, whatever the rest of the methyl phosphate. But yeah, you draw that and you can say plus ortho. Okay. Let's do the multi-step ones. And yeah, here we have a starting material, so a string of reactions here. Benzaldehyde is a meta director, right? And we're going to sulfonate first, okay? And then we'll have that. And both meta positions are the same, right? You have symmetry in this molecule. So it's really just the one product, either or. And then what? The chlorination is going to occur. Let's see, sulfonic acid, is that a meta director or an ortho para director? Let's draw that in. So here's our next product, right? Sorry, that's that intermediate now. Okay. And then what? This is what? This is also a meta director, right? This is a meta director still. So that's the only spot really to put the chlorine on. So our final product is that benzaldehyde that has the two new groups, and everything's mutually meta. Yeah, nice symmetry there. Question on that one? Yes, please. How would I name that? It's benzene sulfonic acid. Um, yeah, so the parent would still be benzaldehyde, and you'd say sulfonyl, and then chloral, but I'm not going to have you name those type of things where you got two complex groups. Okay, yeah. So don't worry. Yeah, okay. I remember from Zoom yesterday, right? You were asking about more of the. Yeah, so some of the nomenclature, we'll keep that simple if there's any at all on test one. Okay. Know the basic parent structures of some of them. And sometimes we use nomenclature in a problem where we just state the name of something, like a multiple choice. We could just, instead of drawing out benzaldehyde, we could just say benzaldehyde is nitrated or brominated, and then you'd have to pick a product. You have to remember what benzaldehyde is. So that's probably the more useful way to make sure you know nomenclature there. But some of these more complex examples, you don't need to worry about it. Okay. How about this one? Phenol. And we're going to do Friedel-Crafts. And that would be what? An ortho or a para director. So that's kind of tricky to say at first which one's going to be major, the ortho or the para. It turns out the para one is major here. It's kind of a big electrophile too. So you get that. That would be right here. And then we're going to chlorinate with excess chlorine. And, we've got the two orthosites. So the excess, and remember, phenols are very good activating groups, right? They're one of the best up there with aniline. And if we say excess and we include the Lewis acid, you can over halogenate. So that one would be what, this intermediate here? So what's our final thing? Here we do HCl with the zinc amalgam. That's the so-called, Clemenson? You could say Clem there. But on the test, I'll draw out the reagents, okay? On your synthesis problem, you could just say Clem or WK, okay? That'll help the graders too. But make sure you're clear on that, okay? And make sure you know what those reagents are. So what do we do here? We would reduce the aromatic ketone, and it's specific for that. The carbonyl has to be at this aromatic position. And you see that we'll put in the two hydrogens, no rearrangements, and everything else goes along for the ride. So you get the dichlorophenol, propyl, whatever, yeah, straight chain propyl. Question on that one? All right, let's look at next panel up. And again, we'll go to the sample test and go through that. Some people already emailed me some questions on that. I was just answering a couple. Any questions on these right now, though? Go ahead.
Is it good to assume that we'll do para first? Because if we have a para ortho, the problem that I was seeing with the homework is I would do it all, but I would do the opposite.
Right. So a question on if it's an ortho para director, do you go with the ortho or the para? And we saw with toluene, right? When we nitrated toluene, the ortho was 60%, the para was 30%. But I told you could easily separate those two and go on. Now that's a methyl group. That's a pretty small group. Okay, and you could say a phenol is a pretty small group. But phenol in general will give more, especially with a bigger electrophile. But again, you don't need to know that. You would have gotten full credit on this problem if you did the acylation at the ortho position and then put the dichloros at the ortho and the para position. But make sure you're consistent and follow through correctly there. There are some alternative answers. And same thing with the synthesis problems. If you mix up the order of how you do things, as long as they're reinforcing of each other. Sometimes the order doesn't matter. We did some examples like that. So the solution manual sometimes just has the one answer. And I pointed that out. I think somebody zoomed in yesterday and we found one that it didn't matter what the order was. Gave the same thing. But it's something to worry about, right? And there, use your scratch paper and consider a couple things. If it's a multiple choice thing, we'll give you one of them as the correct answer. Okay, so kind of have to examine all the others to rule them out. But that's a good question. Yes.
How do you know if the chlorine is going to make a dichloride on the benzene, or it's just going to put one chlorine?
Yeah, so the question is chlorination on this last one we just did. So here I put excess. You see the little EX? So that would be there's multiple equivalents beyond just two even. Sometimes it's hard to just put in one equivalent. And we also have the Lewis acid there. And besides, phenol is a super active directing group. So that's a combination of conditions to do polyhalogenation, do multiple halogenation. So all of the available ortho and para positions can get chlorinated. You can go up to 3, but not beyond 3 because the meta positions are not activated. Okay, so that would require a different thing. Yeah. Anyway, but good questions. So these are combinations, you're starting to worry about. That's good. Here's some going back to chapter 16, I think. Yeah. So the 1,2,1,4 addition to butadiene and the Diels-Alder reaction. We've got a couple here. So butadiene, low temperature. So we're in the kinetic mode here. So we've got to protonate one of the N carbons to give the most substituted allocation. And then the chloride or the bromide has to attack what? The more substituted carbocation position. And that's our so-called what? Not 1,4, but 1,2 addition mode, right? So pick your end. They're symmetric there. Doesn't matter. This would be your product. Is that correct? Everybody in accord with that? We could go through the mechanism, right? And we put the proton out here on the end, you see, and we'll get the secondary carbocation. And it's in resonance with the primary localized carbocation. It's in a molecular orbital. Okay, there's 3 molecular orbitals there. So we draw the localized structures. Those are helpful, though. Those help us keep track of the mechanism and selectivity. So this is where most of the positive charge will be, not so much here. At low temperature, what's faster is 1,2 in that case. If we were at 50 degrees, it would have been move the double bond over here and put the bromide there, right? We would have attacked there. Questions on that? Little review? Yes? Mm-hmm. Yeah, if it's an isolated diene now, you just treat those as regular alkenes from 351. You do the Markovnikov protonation on the end, secondary carbocation, and attack there. So if we treated this molecule with 2 equivalents of HBr, we just get the dibromide there and there, right? So it's different with the conjugated polyenes because the intermediate cation, you see, is resonance stabilized. And then we have 2 different positions where we can attack. That's the difference, yeah. But yeah, chapter 16 has more discussion on that. Oh, and then we got another one here. Let's do this one. So we've got methyl butadiene or isoprene, it's called. HCl, higher temperature. So which end are we going to protonate? This end here on the right or this end on the left? If we protonate on the left, we'll get secondary and primary allocation. If we protonate it here, what do we get? Tertiary primary. So tertiary primary is better than secondary primary, right? So I'd predict we're going to protonate there. Maybe we could do the mechanism. Here we got enough room. Okay, that would be it. At higher temperature, though, we'd want to attack what? The position where we have the more substitute alkene, and that's the thermodynamic product, right? So 1,4 is typical there. So what do we get? So that would be our product. Okay. Yeah. Yeah. So questions on that? Okay. We can also react these dienes with dienophiles. So if we react butadiene here with this conjugated alkene, there's our dienophile for the Diels-Alder reaction. And we've got, the S cis conformations available there. So we're able to do the Diels-Alder reaction and we'll get the product. So everything else will be there, the anhydride stuff. There's our cyclohexene that we formed. These two hydrogens are cis in the starting material, so these two hydrogens here are what in the product? Cis to each other. So draw them both up or both down. Okay. So don't leave it undefined. You might miss some points there. Braden's a nice guy, but when he's grading, he might take off points at that point. Okay. Yeah. Questions on that? Okay, if you go through the transition state, you can see that, how those two hydrogens have to be together. Here we'll have to look at the transition state. Here we have cyclopentadiene with the unsaturated aldehyde here, acrolein it's called. And we can do the reaction and see the connectivity there. And if that's all you put, you get partial credit. But what's the issue here? We have stereocenters now at the allylic positions. And we have a stereocenter here, of course. So what do we need to worry about now? We need to analyze the transition state. And that's the tough thing, I think, about the Diels-Alder reaction. So let's do this. Let's put the molecule on its side here and see where our pi bonds are. And here's our pi bond of our aldehyde. And I'm going to put the aldehyde tucked underneath the diene. Why am I doing that? That's the so-called what? Endo rule, the dreaded endo rule. Okay, we have to look at that. And here's our bonds that we're making, right? So a little easier to see here, right? Because there, we didn't have that bridging methylene here like we do on cyclopentadiene. And I brought my models to look at that. And if anybody has some, and that's always the best way to look at this, examine models. You have to go through it a couple times, if this is a challenge for you. On the chalkboard and paper, we're limited to 2 dimensions, but these are 3-dimensional objects, so the stereochemistry can be tricky. We've given you another resource to help out with this, Chem352, those animations online. Go to Chem352 and look at more of the Diels-Alder examples. That's a great way to keep track of these, but what does this really mean here? Well, we've got these p atomic orbitals, right? These are the things that are interacting here. This is forming the new sigma bonds, right? So you have to look at those. The carbons go from sp2 to sp3 hybridization. So when we generate stereocenters at the allylic position and here, we have to have the relative positions to each other straight, right? So let's see, this hydrogen right here and that methylene in the transition state, what are they? They're cis to each other, right? Because we've got the carbonyl of the aldehyde tucked underneath. That's our endo rule. That's our secondary orbital overlap issue that the book says that's more favorable to have it tucked underneath because you have some extra pi interactions, okay? So what do we get here? Well, as we've drawn it here, that bridge will be up, and this hydrogen will be up. Now, maybe if we redraw this transition state, draw the product with the same geometry, maybe we'll understand this cis relationship a little better. Okay, let's look at it. Here's our aldehyde tucked underneath our hydrogen, their double bond there. Okay, so here you see hydrogen and methylene, right, coming out of the transition state. Aldehyde's still tucked underneath, and when you pull that out, what do you see? See this hydrogen up? We could draw this line back. We don't have to, as long as we draw one line back, one line, the other line's opposite of it. And this shows that we have the cis relationship between that hydrogen and that methyl right there. But if you understand the transition state, the endo rule, you can apply that to any variation that we might give you, okay? This is a common variation. Cyclopentene, penadiene's very common. Diels-Alder diene, very reactive. So there's a lot of good examples with it. We did a couple others in class. We examined them the same way. We looked at the transition state, and we looked at tucking the carbonyl here that's activating this, making this a better dienophile. We tuck that underneath the diene of the Diels. So maybe if we look at the models here, should we do that real quick? We can look at this. So here's cyclopenadiene. Okay, here's that methylene that's circled right here. There's two hydrogens on it. But I got the pi system, with the shading there, conjugated. And then we've got the aldehyde here. The red ball is your carbonyl of the aldehyde. And so for our transition state, we'd want to have pi bonds coming together like this. And so I'm holding where the d sigma bonds are. Okay, and then this little guy here is the hydrogen. Oh, there went my aldehyde. Okay, that's all right. It's pointed down still there. So if we do that and run that reaction, Chem352 does a better job of this. We get this, and you see we'd have the aldehyde down over there, and this hydrogen here is cis to the methylene, and that should be that same drawing there. We have the new pi bond back there, that was the C2, C3 position. Aldehyde down and methylene up, hydrogen up right there. Now, this is a chiral molecule. We can form its enantiomer very easily, okay? We can do that a couple different ways. We can react on top now instead, but still endo. See, the aldehyde's still over. That will reverse all the stereocenters, okay? And give this just opposite with that down and this up now, okay? However you want to tumble it in space. To draw the enantiomer of this, we'd have to invert all three stereocenters, okay? And that's easily done just by flipping over, changing the mode of how we bring the two pi systems together, okay? That's the trickiest concept stereochemically, okay? If you want to come up here and play with the models, have your own model set ready to go to take over the testing center if you don't quite get it, but go through a couple examples and make sure you're clear on that. Questions? Okay. I have a couple more. We have some synthesis problems we could do, or should we get to the sample test? Let's go through the sample test, and then maybe I'll point out a couple that I'll do at the board also. Okay, and if you've got questions, yes, please. Oh, yeah, we didn't get to that one, did we? We left one up here, undone. Let's see, what is it? Oh, so the methylbutadiene one, and then the alkyne, okay? So let's see. And let's put the methylbutadiene right there, and let's do the Diels-Alder. And that's helpful, push the electrons around the ring. You have to have S-cis. And you can see there, your cyclohexene you're going to form is right there, your methyl group. And then what else is there? Well, we still have one pi bond. We just use one, the alkyne. Remember, an alkyne has two pi bonds and a sigma bond, right? That's the triple bond. And then the esters end up here and here. Okay. So that would be your product reacting just with one pi bond right there. Okay. And because the diene, comes together like that, there's no way you could draw these trans to each other. Then you'd have a trans double bond here and a cyclohexene, and that would be impossible physically. Try it with your models, but yeah, they have to be out there. Okay, let's go through the sample test briefly here. I think we're okay on this first page. Yeah, Braden, if you can see that. And I've got it in page view mode here. I think it's bigger than showing it in full screen mode, but have the sample test. You have the key to it as well. Okay, so some people have asked about a couple problems. None on this first page. I think we're okay. Not aromatic, cot there, cyclooctatetraene, because it's not flat, right? It'll pucker. And I gave you the NMR data on that too. It's about 5 ppm, so it's clearly not in the aromatic range. All the others are aromatic. Resonance first. Oh, some people asked about this. And this is a homework problem as well. This ester is in the middle of two benzene rings. Notice this side, the carbonyl is conjugated this way to make it deactivating in that ring. So that's slowing down reactivity. And that would be a meta-director. If it went in this ring, it would go at the B position, right? But if you just have one equivalent of bromine and just doing one bromination here, it's going to go over here. Why? Because it's conjugated through the lone pairs there. Okay, we didn't talk about these dibenzene compounds, but some functional groups we can have benzenes at different positions, right? And we can think about how that might do electrophilic substitution. So it's this one right here at that para position. Okay, someone was asking about aniline earlier upon nitration. Well, that's with nitric acid, sulfuric acid. That will protonate aniline and make the anilonium ion, right? The ammonium cation. Aniline is basic, right? It's like an amine. So you protonate that, and then you'd get a meta product via the anilonium ion. There it is spelled out. All these others aren't correct. Orthopara, nope. Okay, remember, strong acid conditions, that's a problem. Nitronium ion can't form. No, that can easily form with this combination. Paraproduct due to hindrance. No, that's incorrect. Examine each one, each answer carefully. Use your scratch paper if you need to. Go back to structures. That's always good. I mean, the words are okay, but that can easily lead to confusion. Draw out, the structures. Use your scratch paper. That's always good advice, I think there. We talked about that one, 12. I think application problems. Some people are asking about that in Zoom yesterday. Do you have to memorize every little application? No, but know the principles. We covered retinal in the eyeball a couple times, chapter 16 and polyenes. So that application here is an important one biochemically, and retinal is the only one that's a polyene in this case, okay? So know a couple of the applications. We won't have a lot of those type of problems, but you should know why we're pointing out certain things in certain ways. I always point it out relative to a principle in class, though, okay? So don't try to memorize a bunch of the biology. Yeah. Number 12, okay, so alkylation. If you alkylate benzene once, sometimes you can get polyalkylation because what? Once you get one alkyl group on there, it becomes more electron rich. So the second alkylation is faster than actually the first one with benzene. So you have to limit the temperature and the equivalence. You can get monoalkylation, no problem, but you have to be careful of it. One of the problems is overalkylation. Okay. Yeah, HOMO, this is the HOMO of butadiene. It's all the above, I think, yeah. Oh, NMR. We won't have NMR. You could do this one. The answer is D. That's parachlorotoluene. The toluene resonance right here around 2. If this was an anisole, that would be directly on the oxygen. That would be 3.5 ppm. So yeah, I already told you don't worry about that. Dr. Bronson covers NMR very well now in 353, so I've decided not to add that on. But work some of those problems, to keep your NMR skills up there. We mentioned NMR, though, in the context of aromaticity, the ring current, and that's why you get the shifting down around 7. So we can't leave out NMR entirely because it has to do with the unique structures of aromatic compound. Okay, and no benzylic oxidation if it's tertiary, so A right there. I think that one's okay. Low energy conformation is the trans. You need the cis, though, for the Diels-Alder. Okay, so a little on the conformation issues. Oh, some people were asking about aromaticity. When do you know when it's flat or not? And then it would be non-aromatic, right? That would violate criteria 1 of the Huckel rule. It's not flat. It's got to be continuous, right? In a ring, whatever, fully conjugated, sp2, blah, blah, blah. And then criteria 2 is 4n plus 2. This has 10 pi electrons. That's okay by criteria 2. But it violates criteria 1. Why? Examine the structure. These two hydrogens pointing right at each other. No, you can't do that. It'll pucker that molecule. One will be puckered up, one puckered down. That will make this not flat. And if you look at the proton NMR, it's around 5 ppm. So it's a non-aromatic polyene because it's not flat. Yeah, it's got to be fully flat. This one here is Diels-Alder. I think you just zip it apart right here. Just draw a line right there and push the electrons back. And you get to, I think, that. C, yeah. And then your methyl group there next door to the ester. And look, they're trans to each other. So there you go on that one. Uh-oh. Am I not seeing the rest of it? Oh, a blank page for some reason. And then these ride-on ones, people were fine with those. I think you could go through those. Those are usually just simple one-step reactions. Sometimes we put a two-step thing in there. But all those, I think, were okay. These are a little trickier, and that's a different way to ask reaction problems. Provide the starting material. Then you have to examine the reagent, see what it came from. But most people were fine with those, too. Anybody here have a question with those? I think we're okay. This is maybe a trickier one right here. So here's your over-alkylation problem that somebody asked about. And if you treat this as excess, you can get this as a major product, the tri thing here. So you get 2 on there, and then another one goes on. But then if you heat it up with acid for a longer amount of time, you can actually get it to isomerize to the all-meta product. So what's up with that? So you have to reprotonate the ring and do a shift. And why would it want to shift to this? Why is this a thermodynamic product? Because they're all far apart from each other, right? Here you have the 2 methyls right next to each other. If you make a model of that, the hydrogens are actually touching in some conformations. But electronically, that's favored. So you call that a kinetic product for over-methylation. But you can protonate the ring and do a methyl shift and get the more stable 1,3. Now, that's a harder problem. So I explain all that here in the question. And then we try to lead you on and give you some hints about how this might work. It's kind of similar to that taking off the sulfonic acid. You've got to protonate the ring. And instead of taking off sulfur trioxide, you shift the methyl group over. Okay, so I can show you that on the board if we got time there. This one here looks like a harder synthesis problem. But if you realize, oh, this is an aniline, look, I could put the orthobromo and the parabromo on at the same time. And then if I need to put this chloro on to begin with, look, I'd have to have this aniline, not as an aniline. I'd have to have it first as a nitro. So you'd want to nitrate first benzene, then do metachlorination as a nitro group, then reduce to the aniline using your hydrogenation, hydrogen, palladium, or HCl tin, and then bromine, okay, with FeBr3. So that one looks tricky at first, but if you try it and start doing some things backwards, you'll see how it maps right on to nitrobenzene. Question on that one? I think it's okay. What's that? Can I name that? I can. That's not part of the question here. Oh, it says provide a name. There you go. That's why we're asking. Sorry. So how would you name that? It would be 1,4,5, I think. Yeah. So what would it be? 2,4-dibromo 5-chloroaniline. Did I do it? I don't know. Okay. Yeah, the question is, does it have a correct name or can I name it? Those are often 2 different questions, right? Okay, no. No, okay. Oh, okay, yeah, cyclopentadiene, and this is a frost circle, the inscribed polygon approach. That's described in the book, and I show that in class. We have the handouts for that. But no, the frost circle thing is covered very well, I think. If you have all the molecular orbitals fully filled below the halfway point, then it can be aromatic. If they're half filled, or if they're at that halfway point, then it's anti-aromatic if it's flat. Okay, it's got to meet the first criteria for Huckel rule. And let's see, worksheet problems. We'll defer on those if you got questions on those. Let's do a couple more on the board here, and then do some of the harder problems maybe. Yes, please. It's asking about what? Uh-huh. Define the character. The last problem? Right. Is it aromatic or not? Is it well behaved or not? And yeah, the cation would have two of the lower orbitals half filled. The electrons spread out if there's equal energy orbitals. That's Hund's rule. And then if you have half filled molecular orbitals below the line, then it's anti-aromatic. Yeah. So if it's at or below and half filled, then it's anti. Yeah. I can draw that out if you'd like, but let's do a couple of these. I have a couple more here. Let's see. How about this one here? Uh, oh, synthesis problems. Yeah, we haven't done any of those. Well, we looked at some on the test, but how about this? And here you're told you can start with anisole. And that's, we don't know how to make everything. So if we have a group there, that we haven't done, you'll often be given that. So here, let's analyze our product. We got to get to that and propose a synthesis. So the alkene here, we're going to put in as a propyl group. We're going to have to do our benzylic halogenation and the elimination, right? So there's a couple reactions that are peripheral to the other five that we need to think about there. And then this is a straight chain primary. So we really need this to come from what? So our analysis should include how we're going to get that group on there. So it's going to have to be Friedel-Crafts acylation, right? And then reduction, okay? So we're already kind of figuring that out. And then, what's the direction here? Well, that's para, that's good. Our methoxy group would be an ortho-para director, okay? And then this is ortho. So we can kind of see how that's going to go. And it looks like we could do all this stuff at the end then, right? So let's see, what would you want to do first here? How about Friedel-Crafts acylation? And here, you probably could switch up the order here, although that acyl group's pretty big. I'm not sure if ortho or para is dominant here, but we want the para. So with this big group, we'd at least get a good yield, I think, of this. And like I said, you could probably do the chlorination first and still get full credit. And then they're reinforcing. Here's an example where those two groups on there would be reinforcing. So we can get this, and then what? Chlorinate. And you need to analyze this, right? This is ortho director. Oh, and this is a meta director. So you'd not want to reduce that yet. Then you'd have these in conflict. Okay, you see that? So don't do the reduction yet of that. You'd want to chlorinate. That would really enforce this, give you the best efficiency for this. Okay, we good so far? Questions so far? Yes, please. What's no, because I think this is a better director. This is a better ortho para director, right? Because the lone para. So you probably wouldn't miss point. But if it became where they were out of conflict and this one was more dominant, then you potentially could. So examine it. Use your scratch paper to consider a couple pathways here. I'm kind of jumping ahead to the major pathway here. And then what do we need to do? We need to reduce. So HCl, zinc, mercury, and then brominate with light. Oh, I can just do them all, I think. T-butoxide. Sorry, you could draw intermediates for each one of those. And on the test, it's better to do that, okay? It's easy to mix some things up. But there you would want to reduce this to this. Well, we had them up there, okay. And then brominate to this. And then that's the guy that would lead to the alkene. And it's good. It's the trans alkene. That would be the stable one, okay? And there's really only one place we can do the elimination right there. And there's two hydrogens there anyway. So yeah, the E2 would be fine there. Question on that? That's a tricky one because it has multiple peripheral reactions associated with it, and it's got some, you know, directing effects that are kind of tricky. Yeah. Nothing. For the purpose of our class, nothing. It's a free radical process, so we're shining a light on it. Okay. And we don't have this alkene yet, so we're not halogenating anything. And you could say, well, this is a strong activator. Maybe it could brominate here. But you don't have a Lewis acid there. So we're doing, you know, room temperature photolysis. We're reacting it with light, photolyzing it. And then it's in the radical pathway here. So that will do the benzylic halogenation selectively. Yeah. Yeah, so some of these reactions, you can kind of see some other reactivity that might occur, and that's why all the reactions aren't always 100%, right? There are some other things that could happen off the pathway we desire. So it's a good thing to worry about there, but the light conditions with bromine or NBS, like was pointed out, will do benzylic halogenation selectively. Okay, let me show you a harder problem here. And people always ask, well, give me some harder problems. As if you don't have enough problems already, right? Why do you want me to give you more problems? Okay. Well, here's one I think that's kind of neat. It combines the Diels-Alder with electrophilic aromatic substitution. Let's see if you can get it. Here we have an alkyne ester like we saw before. So draw that product. Then we're going to treat with sodium methoxide. There'll be another intermediate here. And then we're going to treat with nitric acid, sulfuric acid. And we give you the product on these harder type of problems. Your job is to come up with the intermediates here and figure out where things came from. We could ask you about the mechanism of all of these. But that looks like a harder problem, doesn't it? Because we got this nitrobenzene ester. We don't see any benzene to begin with, right? So what's up with this? We need to go back to the beginning and analyze, maybe step back here. We could go backwards here and think about this. That nitro group went on, that's, you know, nitration, right? And oh, look at that. Here's an ortho paradirector, and here's what? A metadirector deactivator. We go with the more active director, right? So that would be maybe this position here. So maybe that's our last step, question mark. Because we don't know if we can get to this yet, right? We need to analyze from the forward position. So what would we do in the forward position to figure this out? Maybe what? What does this look like? I've drawn it in the right conformation for you, right? Is this S-cis? Yes, it is. It has two chloros there. We only have one chloro in the product. Where'd the other chloro go? Well, let's analyze what? What product is this? What reaction is that? Diels-Alder. Yeah, so push the electrons, and let's see what that product looks like. It looks like this. Chloro. Not worried about stereochemistry yet. Maybe we don't need to worry about stereochemistry. Oh yeah, because this is an alkyne. Look, we don't have any stereocenter here or here. These two chlorides would be cis to each other, but maybe we don't need to worry about that. Well, what's sodium methoxide in there for? That's the real question, right? Can this go to this? And how? You would eliminate, right? And which one do we eliminate? This one or this one? If we pull that one off, look, the chlorides would end up ortho. If we pull this one off and eliminate this one, then that one would stay there, right? And notice this hydrogen here is at the gamma position relative to the ester. In fact, let's pull that proton and leave behind the pair of electrons and see what we get. So we'd have that chloride still there, pair of electrons, little bond, ester, and we still have this chloride here. We haven't operated on that. But look, we have an anion now, right? And look, we could resonate that up to this carbonyl. This turns out to be the more acidic hydrogen. And with one equivalent of methoxide, look, we get to this thing we need for the final step. Okay. So yeah, push the electrons here and eliminate that chloride. And look, that gives this, I think. Yeah, okay. So this is a harder problem, but actually we could figure this out. Doing what? The Diels-Alder first? Thinking about the E2 elimination of either of these chlorides. This is the one we need to get rid of because we need to leave behind the meta one, at least by the dictates of the product you're given. You're given that product. We're not asking you to come up with that product cold. And that's what some of these harder mechanism problems are. You have to analyze it and map onto the thing, you know, where's benzene coming from? That's a good question if we're going to nitrate. And then how do we get that? Well, we can get a six-membered ring here if we remember the Diels-Alder reaction. Well, then we got to get rid of one chloride, and maybe this base does it. So can you see logically how you might wend your way through a problem like that? I don't know. Is that a harder problem? Yes. Okay, our test won't have a bunch of those. It might have one like that, where you've got to combine different ideas and think about it a little more critically. Yes, please. Yeah, presumably. And it aromatizes, right? If you pull this one here, look, you have anion here, here, and here. It's never right there. But if you pull this proton here, then you have anion there, there, and there. And that's best for, well, let's do it. Let's do the resonance structure. I just mentioned it. So why that bottom proton coming off, you can see, you'll get this. That chloride's still there. And yeah. Yeah, you can see that. And then we can eliminate this chloride by going all the way around the ring. Look at that. Okay. The magic of OChem. Okay. But yeah, this pKa, I don't know, it's got to be at least lower than 15 or 16. Methanol has a pKa of about 16, 17. So this pKa is probably around 5 or so. So after the Diels-Alder, if we treat it with a good enough base, we'll eliminate that one and allow for elimination of that chloride to give that product. Okay. Good enough on that one. Is there one more we want to do? Let's see. Oh, how about an industrial process here? You guys use this stuff all the time. This is a common detergent. It's this. One, two, three, four, five, six, seven, eight. It's a sodium sulfonate, benzene, straight chain octyl. That's not the real name. It forms micelles. It's a detergent, surfactant agent. It cleans surfaces, right? You can form a ball with this, with all these nonpolar things buried in the middle, and then the sulfonate is water loving, hydrophilic, so it'd be on the surface of the micelle. And in the interior, the dirt and grime and everything would want to partition, then you could wash it off. So it's similar. We talked about micelles before, I think, and how they function as soaps or detergents, these synthetic things. How do you make this? Make that from benzene. And if you come up with a good process, you can make millions of dollars. How do you do it? Well, we know how to alkylate, we know how to acylate, we know how to sulfonate. What are we going to do first? We're going to react it with this, right? 1, 2, 3, 4, 5, 6, 7, 8. Why am I doing Friedel-Crafts acylation? Why do I have a acid chloride there? Because it's straight chain. I want to do the straight chain without rearrangements. So that would give me this benzene ketone, 2, 3, 4, 5, 6, 7, 8. Okay, good yield, high yield. You got to have high yielding intermediates if you want to make money in this business. And when you're doing it on ton scale, it better be reliable. This reaction would be reliable. And then what? Let's see, we need to sulfonate, but what should we do here? If we sulfonate this guy directly, we'll get the meta product, right? So we need to do the Clemenson or Wolff-Kishner, okay? And that will give us this. And then what? Sulfuric acid, sulfur trioxide. In industry, they'll use more sulfur trioxide and less of the acid. It's just a little easier to deal with. Small scale, you can all use sulfuric acid. But there's one last step here. This will give you the acid. The last step is this. Why do we have to treat with sodium hydroxide to give the actual detergent? Because we need the salt. We need the sodium salt. And so the byproduct there would be water. We could dry the water off and then have the detergent and then add that to whatever our formulation is for our cleaning agent. But yeah, that's a modern detergent. It doesn't have a phosphate in it. So if it is released into the environment, it won't be a nutrient for algae to grow in streams or lakes. That's a real problem. In the old days, detergents, soaps were based on phosphates. And when those are released in the environment, the algae can bloom, and then you get deoxygenated waters, and that can be toxic to a lot of things, fish and other organisms. But yeah, so this is a complicated problem, but it's solved using some chemistry we're familiar with here. And I think that's it. If you got questions here, you're live. Come up. We can talk a little bit. If you're online, of course, watching the video, shoot me a question. The key is posted for the sample test. You can look through that, and you should be okay. So good luck on the test. You should be fine. We'll see you on Monday. We'll remind you of the closing time on Monday. A lot of you will be taking it Monday, but be aware of that closing time. That's an important thing. All right, very good.